All right. Good evening one more time. So we're starting right in. So today we are going to be talking about deep learning, and just as we have discussed in the preliminary part of the training, the on the day one where we introduce ourselves to the overview of the whole machine learning. So we told ourselves that the real deal in machine learning is really the deep learning, because that's where we have a lot of real intelligence in terms of, let's say, voice recognition, image recognition, image classification, language processing, natural language processing, the language translation, video processing. That's the neural network. Deep learning is actually where the real thing is. So the nature of this class is that we have a couple of but we'll manage it to ensure that we keep it simple as much as possible, while also not being too simplistic. So we'll see how that goes, how well we can get that done. Alright, so without much ado, I would just jump straight in. So we need to install a couple of things. So there are a couple of things that would a couple of tools that we are going to be using for this exercise.
Sir, I hope you are not talking. We can't. I think you are muted.
Oh, you are not hearing me?
We can't hear you.
Or I'm muted on. Seriously? Seriously. I've been talking since. So let me take myself back. So good evening one more time. So we're just going to be jumping straight in. Alright, so just as we have discussed on the day one of the training, where we did overview of the artificial intelligence and machine learning. So we said at the time that deep learning is really where we have so much advancement in machine learning, this is where we have voice recognition, image recognitions, classification, language processing. That's really is a real deal, basically, and that is what we're going to be doing today. We're going to be introducing it today. We're going to be introducing deep learning, and we'll see how far we can go while keeping it simple, without being overly simplistic. So we'll see how far we can go. All right, so for us to do this, there are a couple of tools that are required, which are frameworks that are used in deep learning. So we're not going to be just coding it out from scratch. So the frameworks that are used are really a lot. We have MXNet, CNTK, Cafe2. All these frameworks are available, but the most popular frameworks that you see out there are TensorFlow, originally developed by Google, and Keras, which is also built on TensorFlow, and of course TensorFlow have a cheap version of it. And then we have the simplest one, which is the PyTorch. So these are frameworks that are used for deep learning, various frameworks that are used for deep learning. So I'll mention them again. The popular ones are TensorFlow, Keras, built on TensorFlow, and of course the PyTorch. There are other ones like MXNet, CNTK, and Cafe2. But those are not so popular. Alright, so without much ado, we're just going to install those. so that we can get it in. So to install them, you have two options. Most people in Python development ecosystem generally, it's a good practice to have some sort of virtual environment for a couple of Python applications that you built, so that, or you're building, so that if um, certain application requires certain package, or certain, like, let's say it requires a numpy, and it requires a certain version of that sub package, for instance, a certain version of numpy, and this other application requires different version of numpy. So it allows you to, virtual environment allows you to be able to manage version conflicts, so that you are not working, everything is not working on the same box, like that. So you can create a virtual environment and have everything installed in there. So, but our approach would just be to install our approach would just be to install everything, on this box here. Please, am I still connected?
Yes, you are very loud and clear, sir.
All right. So, moving on now. Yeah, please, 1 minute. Someone just call. 1 minute, please. Let me quickly. All right. So, okay. So we're going to jump in and go straight to installing these packages, TensorFlow, and then we install Keras. They have their own prerequisites. That's what you need installed before you can install them. But when you're installing, it's able to get its requirements and get it installed. So a couple of requirements are we already installed. Okay, can I move down my sharing bar? Okay, it's covering. Thank you. All right. I did it again. All right, so the so let's get that installed right away. So the first thing we want to do is to install our pip, because Tensor requires the latest version of pip. So if you have old pip, you may want to upgrade your pip package. So you're going to do pip install and then upgrade pip. So you upgrade your Python installation package or install package. So do that so that we ensure that we are having the latest version. So in my own case, my requirement is already satisfied, so I have 23.2.1. So if yours is not up to date, so you're going to have, you have some, upgrade, and then it will install. Then, please, are we following along?
Yes, we are, sir.
All right, so the next thing we're going to do will be to, install TensorFlow itself, which will be pip install TensorFlow. Pip install TensorFlow. So you do that to have our TensorFlow installed. So you can see in my own case, say requirement already satisfied because I have it installed. So if you don't have it installed, you would, you'll see the installation will go on for a while, and then you'll have it. So the next thing you want to do after that installation is to install Keras. So you can install Keras as a separate package, or through you use Keras through TensorFlow. They are actually independent framework. Keras is very beginner friendly, and of course it's built on top of a TensorFlow, so it just simplifies it, make you a bit more productive, so you focus on what you want to do rather than bothering about the complexity of the model. So hopefully we have run that. The next thing you're going to run will be pip install Keras. So pip install Keras. So, and if you're using Anaconda, you're going to be using Conda instead of pip. So in this case, I already have it installed. So, and you can see that it says that requirement already satisfied. So I just installed the necessary package, the framework to be used, TensorFlow and the Keras package. Alright, so a couple of things to remember before we jump into writing the code. On day one, we have this diagram in one of the slides which explains the artificial neural network. Or of course, we said that this mimics the way the human brain works. So human brain has about 68 billion neurons, and all are interconnected and all work together to achieve to make the brain powerful. So the same thing, artificial neural network. So there is everything is in layer. This is model. All of this together is called model. All right. So, and this model has layers. So if anybody asks us what a model is a combination of layers. And there will be an input layer that takes in input into the system, and there's going to be an output layer, where result is gotten. And in most cases, you can have one single input depending on the complexity of data you're working on, or you can have multiple input layer. And of course, most of the times you have several hidden layers. Hidden layers are layers that are in between the input layer and the output layer. Alright, so when you build your model, you first of all had the input layer where the data comes in. So the data can be a text, can be an image, can be a video. Alright, so depending on what you're trying to process, but all of them would come into the system as a matrix. They'll come into the data, whether it's image, whether it's video, whether it's a voice, whether it's just a text. Everything will be converted into a matrix form, and then it comes they will have a shape. Each of them will have a shape, and this shape will be taken into the system, and that is called the data shape. So each data has a shape, so you can get the shape of the data, and it's part of the parameter that you're going to pass into your model. So first you're going to define what your input layer is. So there are different layers. Each of these layers have name. You have input layer, most times are called dense, but there are other layers you can also use dense in in inner layers. So you define your layers, input layers, and you're going to define how many neurons you should have. You're going to define the number of neurons that should have for each of the layers that you create. You're going to define number of neurons that they have, right? And of course you pass in the shape of the data. For input layer, it's very important that you pass in the input data. So the input of this layer, of the second layer here, is going to be the output of the first layer. So the input of the hidden layers, as many hidden layers you have, the output of one will be the input of the other. So pretty much the same way the human brain works, the human neurons works. When one neuron finishes processing certain data, it passes on to another one, maybe through axons and dendrites and all of those things like you did in elementary biology. It's the same thing here. So it is important that we lay that foundation. Once you remember, or you refresh, or you have that knowledge, a bit of the knowledge, then it becomes easier to code out. You are not necessarily cramming your way through the whole thing. So this is what we are building. We build a model, we create a layer, we put in the data, the input data, the type of data that it is, the shape of the data, how many neurons. We wouldn't know the input of this one, so we'll leave it to this guy, so it does all of those by itself. So the output of this would automatically be the input of this. The output of this would automatically be the input of this. The output of this will automatically be the input of this. And of course, finally, you have your result here. All right. So for all of this that is going on, there are a couple of guys that ensure that things are done right. So you have some police, you have some some motivator, you have some those things like that. All of them have names. You have regularizer is pretty much like a police that ensure that things are done right. And then you have optimizer ensure that things are optimized and performance are good. You have activators are things that start things up, and activators pretty much determine. So sometimes when data come in, not all data are good. So activator, there's a lot of mathematics going on within the activator that it determines which data should be used to learn and which data should not be used. So it looks into the data and then filters out couple of unused, or not so useful data, data part from the data, from the input data, and then uses that. So I'm not going to bore us with so much theory of this, but as we will progress, I'll be bringing those things up one after the other, and then we're going to be talking about them. So when you build your model, you may want to talk about the activator that you want to use, which regularizer are you using, which loss function are you using, all those things like that. Those are stuff that just ensure that things are done quite right, because neural network is pretty complex, and most of the times is unsupervised. The learning is unsupervised, pretty much like so you can have image classifier. So this stuff can neural network can determine pattern, unlike supernatural supervised or non-supervised learning in ordinary, without the deep learning. you know in deep learning neural network can actually recognize pattern within data by itself, and then be able to do what you maybe is going to be classification, maybe it's going to be translation, maybe it's going to be recognition, maybe whatever you want to do. But we are going to start simple, just like we have always done, so that we don't see everything complex. We're going to start with a simple regression. But when you're using a neural network for a simple regression, it looks like an overkill. It looks like an overkill, but it's the one that gives the most accurate, prediction if you're using it to predict. Although, it might seem complex, like you're using a hammer to kill a mosquito, but then, you use that to start up, and then we can move into image recognition, voice recognition, all those things like that, translation, text generation. So text generation API, just like ChatGPT, is a text generation neural network, which uses a transformer model. So we can. So this is pretty much the structure of everything. The structure of everything that we are working with. All right. Now, so moving on now, having laid this background, the next thing we're going to do is just to continue to fire up our Jupyter Lab. Go ahead and fire that up. Let's have. Okay, so I'm going to have, let me create a new notebook. And let's use Python 3 kernel as always. So the first thing we want to ensure is that all our packages are installed properly and they are ready to be used. Alright, so the first thing we're going to do is to just do sample imports and see. So let's say we import something from here, from Keras, import backend, or import Keras, and then you can use backend from there. From Keras, import backend. All right, so let me explain again. Keras is a framework. As I have mentioned earlier, is a framework and it's standalone. Then he's able to use two types of backend. One backend is called TensorFlow that we have installed. He can also use Theano as a backend. Theano is spelled T-H-E-A-N-O, I guess, like this. So Keras is able to use Theano and TensorFlow. So after the class, you can also install Theano, and then, or Tino, depending on how you call it. So you can have that. Keras is able to use that kind of backend. So that's the powerhouse that he uses. So it's independent, but although it's bundled, if you have TensorFlow installed, TensorFlow encourage. In fact, if you go to TensorFlow website, they encourage you to start from Keras, and he said, in fact, all users should start from Keras because Keras is simplified and it makes you more productive faster. So import backend. So you may want to know which backend your Keras is using. So if you from Keras import backend, and then if you come here, let's say I import that backend as B, and then if I do backend dot backend to see which backend I'm using, if I run this, all things being equal, I would see TensorFlow. Please, are we off coding along? I expect to see TensorFlow.
Yes, we are, sir.
Okay, great. So I'm going to import I'm going to import TensorFlow as well. TensorFlow as TF. Okay, so we're going to be needing TensorFlow, and then of course Keras as well, although what I just imported now is just the back end of it. Okay, so here I have the TensorFlow as the backend that is being used. The only person that have it installed, please, you have to be, or the people that have it installed, please give me consent and let me know how properly to fire on. So this is just to show nothing special, but just the that TensorFlow is installed and the Keras installed. All right, so the first thing I'm going to do will be to maybe take this out, just to show all this. I'm going to take this out, so I just import Keras properly, and then we are going to, without wasting time, we're going to be working with Keras data sets online. So if you go to Keras datasets here, if you go to keras.io datasets here, there are a lot of datasets that you can work with. Cipher 10, MNIST, IMDb, Reuters, Boston housing price regression dataset. So this is the one I'm going to be using. This Boston housing price regression, because I want us to start with regression. Classification might not be so beginner friendly, but I'm going to be doing follow-up videos for classification, image classification, because it requires a couple of functions that is not so beginner friendly. So but once we lay this foundation with this, it's easier to grow up to that one. So we're going to be using this guy here, Boston housing prices, housing price regression data set. All right, so we need to bring that in. We need to bring that into our project by importing it. Okay, so we say from Keras.datasets, datasets, imports Boston underscore housing. So from Keras the datasets, import Boston underscore housing. This will effectively import our dataset for us. So the first thing, the next thing we want to do is to load that data set and then pass in our required variables, the X value, the Y value, our training X, our training Y as well. So let's go ahead and load that in as tuple. So we should just say, let's say we call this guy X underscore train, and then Y underscore train, so that's X for the training that you want to use to train the model, and then Y for the training that you want to. This is not compulsory that you name it this way, but it's just a bit more descriptive. So you can just use XT, YT, or training data, training X, dependent. So people use different type of naming variables. So let's stick to what we've been using: X train, Y train. Then we have X text, Y text. X text, Y text. So we're gonna have this loaded from the Boston data that we just have. So you recall that here it gives you how to load the load data function. So you can see here how to load the data function. So I'm just going to go straight and load that in Boston underscore housing, Boston underscore housing. Please, are we on the same page?
Yes, we are, sir.
Mr. Chima and Mr. Suleiman, at least.
Yes, we are, sir.
So we have load data. All right. So Boston housing dot load data, that should load our data for us. So you can see, you may want to check out, you can run this, ensure that you run this guy so all the packages are available, and then let's run this. So it's going to download the data from the Google storage, and then so that data is downloaded. Now you can check out your X value and Y value, X text and Y text, to ensure that everything is pretty loaded. So you can say that, let's say x underscore train dot s underscore train, for instance. If you get that, so you can see that data loaded, and of course you can check out your y train, x test, y test as well, so you can check them out. Okay, so the next thing you want to do really is to ensure that your training data, because this data is really just, you don't even have an idea what the structure of the data is. And most of the times in neural networks, the type of data that you work with sometimes are pretty unstructured. Imagine you're working with video and you're trying to, or an image, you're trying to recognize pattern from one image to the other to be able to classify it. So it can be so random. All right, so for you to be able to, for you to get the accuracy pretty right, you will have to use some sort of processor and transformer. You use scikit-learn processor to be able to ensure that as much as possible, what you are going to be testing or validating your training data, your model with, after you train your data, your model, after you train your model with certain data, you're going to be validating with the test data. So as much as possible, before you even start training, you want to ensure that the training data and the test data are somewhat in conformity. It's not like you are using X to test to judge Y. So if you're going to judge me, you are going to have to ensure that we agree before we even start the learning process. So that's the first thing we're going to do, and it's very important in neural network, because otherwise, everything is pretty random, and so we have to ensure that things go as expected. So one thing we're going to do will be to transform the data set, process the data sets and transform it. So it's called processing. That's the first thing you want. After loading your data in, the next thing you want to do is to ensure that X and Y, the training data and the test data, they agree. Not like it's the same data, but they agree in terms of the type of data that they are, and the type of structure that they have, so that you're not going to be judging your model wrongly. All right, so to do that, we're going to be processing the data. So let me call it process the data. So to process the data, the first thing I'm going to do is I'm going to scale X train. So I'm going to scale X train. So to scale that, we're going to be using the scikit-learn processor. All right. So I'm going to import from scikit-learn, from sklearn, I would import pre-processing. So from sklearn, I'm going to import pre-processing, and then that will be used. So let's load that in. Then that will be used here. So we use the pre-processing, the scale, pre-processing, the scale, X train, so I'm going to scale this X train, pre-processing or scale. Then the next thing is to convert that to scalar, which effectively get out the standard deviation and the mean deviation and standard deviations, all those these things is going to get that. That is what scalar function does. it gets out the standard deviations and it's at the mathematical level, but you don't have to worry so much about it. Processing in core, first of all, you scale out that data, and then converting it to scalar would be the pre-processing still. Pre-processing dot standard scalar. So you see what this guy has. So let's go to standard scalar. This guy, standard scalar, and then we're going to fit that, and that's going to be the X train. So we have that scale X train, and then we are going to, that's processing the scale X train, and then the scalar value, pre-processing standard scalar, which returns the standard deviations and mean deviations. We have that fit S train. So the next thing is now to scale the X test. So scale X text, remember that this is your variable, so you can name it anything. Scale X text, what you are going to be testing with, S text, which is equals to scalar, this scalar that you've got here, which is a transformation, which is a standardization of your training data. So that dot transform is what you want to use. Dot transform. So I hope I expect this guy to give me IntelliSense, but it's not giving me, so but I would use it myself. Scalar dot now it's ready to give me dot transform, this guy here, and X text. So this, in a nutshell, normalize the training data with the test data, using the sklearn processing scale function. All right, so I haven't done that. The next thing we want to do is to build our model. Remember what the model says. This is the model. Model has layers, input layers. In the input layers, we're going to define your data, input data, the number of neurons to use, the type of activator to use if there is any, how it should be initialized, the loss function to be used if there's any, and all of those things like that. So those are what we're going to do. So the next thing we're going to do is to create the model. To create out the model, so let's ensure that we run this so that we're sure that everything is fine. So the next thing is to create the model. We'll create the model. This is the real thing. Now, but creating the model requires you to bring in the model first. You have to bring in the model. We have not brought in any model here. So we're going to bring a model. There are two models here. One is sequential model, which means that each of the layer follow one another sequentially. Sequential model. One model follows the other model sequentially. The other model, which is not so used, of course is used, is functional API. Uses functional API. So when you'll see sequential, or in some instances you see functional. Those are two type of models that we've got. All right, so but most of the times you see in a lot of models you see sequential. All right, so I'm going to bring in my sequential model. here I'm going to load in my sequential model. So here from Keras.models, from Keras.models. So you see here you have models experimental here. So if you inspect the modules, you'll see the ones that are in there. So from Keras.models, I'm going to bring in sequential. Import sequential. Alright, so that's to say that I've brought in the type of models I want to use, and then I will go ahead and run that to ensure that I run that into my memory. And the next thing I want to do is to then instantiate that my model properly. So assuming we call it a model and we have it like this, equals to sequential. Sequential. So we have something like that. So that is your model. So the next thing is just to instantiate the model. All right, the next thing you want to do is to then build up that model, the layer of that model. So let's say the first thing we want to do is to add the first layer, model.add. So model.add layers. That is what you're adding. You're going to be using add to add new layer like that. So you're going to have this. So I'm going to use this layer here called dense. There are several layers. So I'll use dense. So you see dense here is a name of layer. Dense. Okay, now I'm using dense as this first layer here. This is my input layer here. And then I'm going to have to define the number of neurons that. So the first parameter it takes is the number of neurons that is used, and the number of neurons that it uses is the number of features, mostly the number of features in the data set, but not exclusively. But that is that is what it says. But mostly you see a lot of people use random trial and error, but the standard is that there's a lot of rule of thumbs that defines what you should use as your number of neurons. Can you just close your eyes and just use any random number? By standard, you're supposed to use the number of features, the number of variables in your data set. But most of the times you don't even know the number of variables because you don't see the data that you're working with. Let's say you don't, of course you may not see the data that you're working with. Neural network is able to learn by itself. You're going to be able to build models that can learn by itself. You understand? So you see random numbers that you mostly use. You see 16, you see 32, you see 64, 64 and all of those things like that. But by standard, maybe you want to use the number of features, which is essentially the number of variables in your data set. So I'm going to use 64 as the number of neurons. So the next thing we want to do is to put the kernel initializer. So when your kernel starts, it initializes with certain structure. So there are a lot of kernel initializers. You have normal, which is maybe you have it as 1 1. All the shapes would have a value of 1 1. You can initialize zeros. So it means that the shapes will come in, will initialize itself as zeros. So when we mean zeros, we have said that all data coming as a matrix format, whether it's audio, whether it's video, whether it's text, whether it's audio, whether it's an image, everything gets converted to matrix format. And so when it's in this matrix format, you are going to have to say which values are in the position of each of the matrices. So that is the initializer, how you initialize it. So you can say zeros to just all the values will be in 0, all the values will be 1, all the values will be so like that. So let's say we initialize kernel initializer. All right, we set that to be normal, which is of course pretty much default. So the next thing we want to do is to set the activation. I set that time that there are a couple of things that make things work within the neural network model in itself. Apart from the number of neurons that you should use, apart from how it should start up, there are activators are pretty much in charge of dictating which data should pass through, which data should be used to learn, and which one should not be used to learn. It's quite important in the life cycle of a model, and there are several of these activation functions. We have the switch functions, we have the sort match functions, we have the linear functions, we have the sigma functions, and we have a rectified linear unit, which is mostly used. Rectified linear units called ReLU, and then you have hyperbolic tangent function stan. So there's a lot of all these functions used as activator, but like I mentioned, rectified linear unit is mostly used. So the activation function is a mathematical expression that decides whether the input should pass through a neuron or not based on its significance, like that. So if we pass in the activation to be used here, activation to be used here, pretty much this kernel initializer, all these ones like this, they are pretty much optional parameter, but for input shape you may want to define it so that you have some couple of things in place. Activation equals to, like I mentioned, there are several activations: switch max, sigmoid, linear, tan h, which is hyperbolic tan function, and then you have your ReLU. So here I'm going to use ReLU, rectified linear unit. So the next thing I'm going to do is to then define my input shape here. So we're going to define the input shape. The input shape is pretty much the shape of your data, the shape of your data. So this is equally, just like the number of neurons to be used is equally very debatable. So we have input shape, that's the shape of your input data. So first off, let's get this input shape. Now, so let's say here, rather than doing this, let's say we want to get out the shape of the data. String dot shape. String dot shape. So let's say we get that out and see what we've got. So what you see here is 404. So there is what this means. If it is 2 digits, if it's an image, if it's 2 digits, the third digit determine whether it's grayscale, whether it's color, which branches it belongs, and all of those things. And of course, this the value of your data. So but I can tell you for free that this shape will not always dictate the input shape that you have here, but of course there is a way you get out the shape of your data. So if you use this, pretty much gives you this. You can use a CS function or CV. It calls CV package. If you bring in CV package, it's a special package that is used to, of course, extract the type of the function, the shape of data. So you can use CV package, install it, and then you can use that to get out, an efficient package size. So I'm going to use 13 as the input shape rather. So input shape equals to and 13 and nothing, pretty much like this. So do we have all our brackets closed? This opens that, and then the last bracket opens the arch. So that's a layer. What you see here is pretty much like it's equivalent to this input layer that you have here. So you can have several hidden layers. There's equally how many hidden layers are enough. So that one is also there. How many hidden layers are? How do you know how many hidden layers are enough? These are questions that, intelligent questions that you want to ask. How do you know how many hidden layers there is? So the neural network, the model itself is self-intelligent. So once you pass in this layer like this, maybe you use single perceptron, or you're using multiple perceptron. So if you pass in an input this thing, and if that is well processed, and when it gets to this layer, maybe there's no performance improvement, when it's trained, it trains and validates, and it checks its validation, it judges itself by the loss function. So when it gets to a point, there will be it measures its performance as its training and testing. So it will get to a point that it sees that it seems there's no improvement anymore. I'm good now. So when it is good, there's a callback function that you call that just stops all the jumps in and jumps some layers, and then just go to the outer layer. So even if you have several layers, not all of them, but all of them might not be used. You understand? So the question is, what if it is not enough? So if you have your loss functions and you measure your accuracy, you can increase the model. This is a model that you are building from scratch yourself. There are existing models that have been built that you don't have to worry. You can just go use them. For instance, if you can just go and pick a transformer model, you already have the model that your ChatGPT uses. That your ChatGPT uses transformer model. You don't build it, you have it, and you can use it. So there are existing models that are built for different purposes that you can use it. But it makes sense for you to know the theories or the engineering behind building a model yourself. You will be able to use existing model right. Okay, so if you go straight into if I go back to my distance, I've written a layer here. I'm going to add more layers. So if I had one hidden layer, model.add. So this is another layer. So let me put comment here. Add input layer. And then the next thing we want to do is to again add another layer, and hidden layer. So if we had this hidden layer here, so pretty much the same way, if you use dense still, and then we use the same number of neurons up there, so which should be the features or the number of variables that you have in your data. Like I told you, you always see 16, 32, 64. These are star numbers. you have 64, and then activation function to be used in there as well is rectified ReLU. All right, so we have this. Like I told you, these are others are optional. So we have this. We don't have we are not initializing it. The input of this one is automatically the output of this one. The output of the layer will automatically be the input of this one, so we don't worry about giving it an input. So the next thing we're going to do is just to have add outer layer. So the outer layer here, we're going to have model dot add, and then you have dense. Okay, so you have an outer layer, and then you most of the times you see the outer layer is you have it with one neuron. Of course you can have several more neurons, so but you see in most models you have what's it called, one. But linear regression model is a model that I've worked with, so I can give you precisions with this. These are models I've worked with, so so the next thing you want to do is to ensure that everything is well initialized. You want to maybe run your cells, run all your cells from beginning, and ensure that everything is well loaded in. So we are getting close to the promised land. Sequential model dense is not defined, so I haven't even brought in my dense, and I'm using it. So I have to bring in the dense before I can use it. So from Keras layer, from Keras.layers, import dense. Okay, so we import dense, invalid syntax.
You remove the imported.
Oh, okay.
The sequential.
The sequential, I've removed it. Thank you. All right. Thank you. Okay, so we ensure that loads pretty well, and then we can have this guy here. So this model is, well, we have not compiled the model. The next thing we're going to do is to compile our model. The next thing we're going to do is to compile our model. So compile the model. You have built the model, but it needs to be compiled. Compile the model. To compile the model now, we're just going to be using model.compile. So the model.compile has a number of functions. First, we're going to specify the loss function to be used. The loss function is pretty much like it measures the errors between variations, basically, so to speak. So we've seen that when we have sum of square residual, sum of square total, these are error function, to measures of variations, measure of distance from the mean deviation, from the mean, something like that. So we are going to specify the error function to be used. So here the function, we just pick a function, and that function does the magic that measures the error as the layer progresses from one layer to the other, like that. So we're going to specify which loss function to be used, and also which optimizer to be used. Optimizer ensures things are right. To optimization, things just pretty much like a regularizer, ensure that the ensure efficiency. Optimizer ensures the references, and there are several optimizers that we can use, the root mean square properties and all of those things. And then metrics again, we have seen metrics when we are talking about the supervised learning here where we used and whether through the linear regression or logistic regressions where we use accuracy score to measure the accuracy. So the same thing here, when we compile, we're going to specify which metrics to be used for as a measure of the accuracy. So first I'm going to specify the loss function, which is equals to, so there are several loss functions just like every other this thing. So we have the binary cross entropy, rather. You have categorical hinge, you have mean square error, you have Hilbert, you have sparse categorical. You know, but here I'm just mostly you see a mean square error, which is the MSE error. So I have this to be equals to MSE. Please, in your own interest, you can pause the video and take those notes when you're watching through again, because you're not going to see this. So I have this. Whether you use double quote or single quotes, it doesn't really matter. So you have the optimizer to be used. Optimizer to be used, which is going to be root mean square property. So we have to bring all this in. We have to bring it in. We have to bring the loss function in and the root mean function to be used. So let's go back in and bring them in first before we start getting errors. So I'm going to have prompt from Keras optimizer. You know, so you have all these optimizers here. Optimizers, I'm going to bring in root mean square, import RMS property. Alright, so the next thing I'm going to import would be, so I would import that as we will move along. So I would prefer that we use it as at when to. So we have the meaning now. We have this guy here, RMS prop, imported optimizer. Yeah. So the next thing we will do will be metrics, which will be the mean absolute value. So we're going to be using, so you can use several metrics, you can use multiple metrics, and that's why you have this as an array. So you can have more metrics defined as what you're going to use. So we have mean absolute error. You know, so once we have this guy out, I want to arrange it like this. All things being equal, let me run it and ensure that there's no error. Unterminated string literals on line 5. So there is one here is equal to, I want to write here. Missing requires source argument position 1.
Model.compiler. So I wrote model, compiler, I think.
Can you imagine? Dot compile. Alright. So model.compile. So this builds you up your model and this compiles it. So the next thing you want to do is to train the model. The model is ready to receive data, training data. You know, so you build up the model, you compile the model. So the next thing will be to train the model. All right, so the training will go thus. So let's say we we pass in a variable called training, which is equals to the model. So the just like in your scikit-learn, because this is also built on scikit-learn, all of them, you know, bundled together. So you're going to be using fit. You know, in scikit-learn, we use fit, where we pass in the dependent and independent variable for it to learn with. So the same thing here. So the fit, but this one has a lot of other variables that we are going to pass in. So we're fitting in the scale data. This one here, that's the one we're fitting in. The scale x train, that is our x data. We are not just using the x data, the raw x data that we got from the data. The one that we normalize and ensure that what we are going to be judging this guy with, you know, to some reasonable extent is in conformity with what we are training with. Just like you are going for an exam, and you know, your exam will be set from out of the syllabus. This is ensuring that the exam is not going to be entirely out of the syllabus, even though it can be random. But of course, let's ensure that nothing is out of scope, you know, so that you judge your model right, at least at what is learning and what is you're going to be training, what we are going to be testing it with. So basically what we have normalized is what we are using, scale s train, and then we use y train, which is of course dependent variable, since of course this is going to always depend on this guy. So we say while train. So you notice that we don't care about y value here. So y train. Then the next thing we want to do is to put the batch size. So the data is going to be processed in batches, right? It's going to be processed in batches. So, you know, the idea is that you're going to have a lot of data, and each of these data will not be processed at once. You know, you're going to specify the number of time this would run, the number of times the processing will be done. The number of times the process will be done is called an epoch. It's called an epoch. That's the number of iteration. The number of iteration. So the guy is going to divide your data into that number of iteration, and then each time he picks a batch to process. So each batch, you define what size of each batch using the batch size. So when you say batch size, you are defining each batch. This is the data that goes into each batch. But depending on the size of your data, you know, it might not necessarily follow through your batches, because maybe after first to second or third run, the data is already exhausted, and then what is remaining is not up to that. Of course, that is normal. It picks what is remaining. So you have batch size, which is equals to, you put the number of batches that you should run at a time, you know. So you are at liberty to put the number of batch size, but of course you emphasize large number, so you put it like that. So the common number that is used, that you see here, is 128. Of course, you can use batch size, means number of batches, the size of the batch, type of data that it should run in each batch that it runs a learning exercise. Okay, so it does that, and I said that it's going to go through an iteration. You're going to have to define the number of iteration, the number of runs, you know, and that number of runs is called epoch. Okay, so you define epoch. Of course, you may not know the number of size, so you can do this.size and do some maths to be able to get the number of size and divide that, so that you can have batch size, and you can do some dynamic stuff. If you do training.size, strain.size, you'll see you have something like this data. You have something like this, so you can maybe divide it by batch size, so you can have number of runs, so you can do all those things dynamically. But I don't want to bore us with all those basic stuff. So I can have this guy, so h shape, strain for those that will be, so you can use this size to get out the size of the data, which is what got out this guy. You know, you can then use that to dynamically calculate what should be your batch size, or what should be your epoch size. So if you define in this case 500, you see that your byte size and these things would maybe runs, this is 5,000. All right, so maybe it's going to run like 500 times before it exhausts using this batch size each time to learn. Okay, so the next thing you want to is an optional parameter is verbose. Verbose, you can set verbose take 0, 1 or 2. Verbose take 0, 1 or 2, which is the logging level of this training. If you want to monitor the progress, the default is 1, so that it logs the progress of this guy at his learning. It shows the progress, but if you don't want to see the progress, you can set it to 0. So you have 0, 1, 2 like that. So but if you don't define it at all, it uses 1. That's the logging level of the distance. And then you have the validation split. Validation split is pretty much like what we did while we're doing the logistic regression, where we divided our data into the training data set and the test data set. So validation split in Keras in sequential model means that you're splitting your data into the training and the testing data set. All right, so here you can say that if you say this is equals to 0.3 for instance, it means that you are using 30% of your data set for testing. You're using 30% of your data set for testing, and 70% will be for training. Then if you say 0.2, of course you're using 20% for testing, and the 80% will be for the training. All right, so you can have that set out. So if you split that validation split, that splits that. And again, another thing that you want to put in is to define a callback. A callback function is there to ensure that, and I mentioned earlier, I said, how do you know how many hidden layers are enough? How do you know when it's enough is enough that I can just jump into the output layer? So this can happen through your callback, which is can stop your training early. Once you are good, you are good. Just like you're preparing exams and you study to an extent, you see that this is enough for me to to have my hay, and then you want to stand up. You can be surprised that the lecturer will follow the back door. All right, so callbacks, you can also specify, just pretty much like metrics. You can have it specified, you can have it as defined as an array, and we're going to be using the early stopping. So that's we need to bring in from the callbacks. We're going to bring in that early stopping so that it can. So I'm going to bring that from Keras callback. From Keras callbacks, I'm going to bring in import early stopping. All right, so and that's I'm going to use now. Let's ensure that we run that so that goes into the memory, to the kernel's memory, and then here we're going to use it here to stop things out early. So here we say early stopping. So we get that out. Please, am I connected? I hope I've not been talking to myself.
Yes, you are.
Okay, because I have an absolute silence. So we have early stopping, and then you have the we use monitor level, which is monitor which would be loss value. All right, and of course you also define the patience. So you define the patience. So this is patient is equally a random number to be, so it's going to give it a while. It's not going to just see that it looks like this guy, there's no improvement. Maybe after one layer to the other, everything seems to have stabilized. It will give wait for about, a while to ensure that that stability is not false positive. It's not so false positive. So we have,
Hello, sir.
hello, can you hear me?
Oh, yes, 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 we can. For the patience, like, okay, okay, I get it now.
Okay,
Confused.
come out. Sorry, I made mistake. All right, so it means you are really following. All right, so if you run this guy, we didn't close one guy. Something was never closed. I did not close my feet. I didn't close my feet. So it's not callable. Where it is processing. Let me check that out. RG converted type string metrics. Okay, so let me check out the metrics that we're using and ensure that I did not mean absolute error. Mean absolute, so I didn't type it correctly. Absolute error, mean absolute error. So I didn't type this absolute error correctly, and that is why it threw that error. So let's give that a shot again. Yeah, so it logs it and it trains, it learns well, and it logs pretty much the process. So mean absolute error is this, value loss is this, the loss function is this. So that's reduces. The loss function is reducing as it's moving down, the loss function is reducing. So then eventually it's, the loss function started at almost almost at 500 or 600, 557. The loss function is reducing, loss function is reducing, kept reducing, the loss function is reducing. So the more the loss function reduces, the more you get to the promised land. So it learns pretty much until you got to its unit limit. So from 500 and something to this, and then you can see the mean absolute error also reduced, and then the loss for the value loss, you have it stabilized. So you can see this guy, the loss function, when loss function actually stabilizes at some point, so the guy stops, and it means that this guy has learned reasonably. It has learned reasonably. This model has learned reasonably. So the next thing we want to do is then use the model to let's evaluate the model. Let's evaluate the model and see how much of
Hello,
Mr.
sir.
Chima, yes.
Sorry, I'm getting error on running the training.
What did you get?
I don't know whether you just give me an exception.
Read the
Let
error.
me just see.
Read the error. Read the error.
Let me see. He's
Wh-
giving me exceptions and he's
no, read
referring
that
to
error.
false.
That my own too gave error because I typed means absolute
You say
error.
unexpected exception, formatting exception, falling back to standard exception. And the trace back, the files is giving me call files, not the file I'm working with. Let me just see this. You are training. Hold on.
Okay, so
Let me
look at the
compare with
training
mine.
model here. Look at the training.
It's working now.
Okay,
Yeah,
great.
thank you.
Great. Okay, so the next thing we want to do is to evaluate this guy here. The next thing we want to do is to evaluate this guy. So we're going to evaluate it by, so let's evaluate the model. So evaluating the model is, so let's say we have this guy called score or evaluation, which is equal to the model dot evaluate. So we're going to evaluate this model with the scaled text data. You know, it takes in x and y, but we're not going to use the x test from the raw data. It's going to be the normalized one. S scaled, S the scaled text, x text, right? So we're going to be using the scale x text. All right, and then we use the y test, y underscore test. Okay, and then maybe we don't want it locked. We have variables to be 0. Okay, so the next thing we want to do is to that's pretty much it, really. That's pretty much it to evaluate this guy. So we can print out the evaluation, all things being equal. So you can have the score. So you can have the score. So the score has two param. The first one is the loss function, and then the second one is the accuracy. So if you have the score, for instance, if you get the first one out, 0, this is an array. So if you bring this guy out, this guy here is the test, is the loss, test loss, the loss function there. So we have 22.22. So let me put it in proper perspective. So we have the loss to be this guy here, so that we know what we are logging. Run that out, and then we can print out the accuracy. Which is the score. We put the second one, get out. Okay, so that pretty much gives us the accuracy. The next thing we want to do is to predict with it. You know, regression is about prediction, forecasting, and all of those things like that. Like I said, when you use neural network for, you know, prediction, it's going to be more accurate than this thing, but of course it looks very much like an overkill. So let's go ahead with predicting with this. So let's predict with this. So you can have this to be equals to model dot predict x text. So we're going to be predicting with the scale text. So predict with that, and then you get out so done. So let's now see what prediction looks like. So let's print out this prediction, and then we can flatten it. So we have the data that it got, the prediction, and we have it like this, you have it like that. So that's why we got it flattened, so that the empty space, you know, is removed. So if we have it flattened, we can have it like this. So the next thing we want to do is to get out the white test. Y tests, and we can have that compare with so if you see y tests, this is the test value, this is what was predicted. 7.4 is predicted, the actual value is 7.2, not so much of a difference. This is the actual value, this is what you're testing, and this is what was predicted. This one is 18.8, the prediction for it is almost 18. So you see that is within, though you are not, the data is not so organized, but then the prediction is, you know, quite, you know, within some, you know, reasonable acceptance. So which means that your model works well. You may want to improve the performance of your model, maybe by adding another layer. You know, if you add another layer to it and ensure that maybe maybe you want to add another layer to it, maybe you want to increase the number of neurons, you know, and see maybe you want to change the optimizer you're using, you know, and to see if it, but this performs really well. The performance is top notch. As you can see, the accuracy is more than normal. So ladies and gentlemen, this is an introduction to neural network, artificial neural network, and like I told you, this is where we will have the real big deal of the machine learning, you know. So we started small with this, which is using the linear regression. Of course, our training for this elementary training that this is what we'll do, but we'll build onto it. We'll keep, you know, building up onto it. Classification, image recognition, voice recognition, translation, stuff like that, and then we'll see how we can use the transformer model or any other existing models that are really huge, and we can use that to build our own, you know, your own next level GPT. Ladies and gentlemen, thank you very much for your time.